So so the question's about how to think about the Madelung problem. Okay, let's treat this as a two-dimensional problem. Let's have plus and minus charges on 2D, right? So my 2D square lattice is going to look like this. By the way, we should be careful with the use of the word lattice. I'll tell you in a minute. But let's treat these as the atoms. Do you agree that this is a 2D lattice? Yes? Okay? Now we go this way for x, and we go this way for y, and we write out the coordinates. This is 0, 0. Okay, and by the way, let's alternately color them because to show that one is a cation and the other is an anion. This is now a 4 by 4, correct? Let's just treat it as a 4 by 4, but it can be n by n. So 0, 0, 1, 0, 2, 0, 3, 0. These are pairs, by the way. 0, 1, 1, 1, sorry, 0, 1, 1, 1, 2, 1, 3, 1, 0, 2, 1, 2, 2, 2, 3, 2, 0, 3, 1, 3, 2, 3, 3, 3. Do you agree that those are the coordinates? That's how it works. Okay? If it were a matrix, if this were a matrix, you'd start 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. You can also do that. You can just think of it as matrix indices. You're used to matrices, right? 3, 1, 3, 2, 3, 3. Like A11, A12, A13, right? Matrix. And by the way, you know that you can generalize the idea of a matrix. It's called a tensor. So a matrix is a rank. What? What is the rank of a matrix? No. What's the rank of a vector? 1, because it's one-dimensional. A two-dimensional, rank 2 tensor is a matrix. A rank 3 tensor is a 3 by 3 object. A rank 4 tensor would be in 4-dimensional space. Okay. And have you taken any classes that use tensors? Professor Susanna Stemmer teaches a tensor class. Do you actually need tensors for some material properties? So you understand these indices, right?
Yeah.
So here's all you do. You look at all the ones that where the indices sum up to an even number. This one, this one, this one, this one. And you see all the ones where the indices sum up to an odd number. This one, this one. So you can just say, sum the indices. If it's even, it's positive. If it's odd, it's negative. That allows you to identify the lattice site, right? The next problem is to calculate the distance. So what is the distance, say, between 2, 2 and 1, 0? It's just 2 squared minus 1 squared plus 2 squared minus 0 squared. Oh, what am I doing? I don't need this. No, it's x2 minus x1 squared. Sorry. Right? So that's the distance that goes in the denominator.
Yeah.
So when you're doing the sum, so you sit on this side, calculate the distance to everything, sit on the next side, calculate the distance to everything, and so on. Right?
Thank you. Yeah.
Have people already done this? You coded this already? In 3D? You did too? Could you see the convergence of the Madelung sum? You know what surprised me the first time I did it is the idea that you have to go to quite a large structure before you see the full convergence, which already tells you that if you make small particles, like nanoparticles. Here's a question. If you've done this problem, let me ask you a question. If I made a sodium chloride nanoparticle, will the equilibrium distance between the atoms be larger or smaller than in the bulk? It will be larger, right? There'll be less attraction. because you get the bulk number only when you go to a large size. And the bulk number is always larger than the smaller number. That's the order we went. A square, a pair, a square, a cube, etc. Small structures have less of a Madelung stabilization, and large structures have more of a Madelung stabilization. All good? Again, my insecurity. Let me make sure I'm recording. I'm recording. Good. So actually, today we are going to work back a little bit. So what are we going to do? So remember that I've told you that my traditional method of teaching this class is to teach structure first and electronic structure later. But I inverted it this year as an experiment, partly to aid the students who are taking 200A. So I don't know if it's helping. Did you hear my question? Maybe it's not important. But anyway, I'm going to teach structures now. So let's start off, and of course, by the way, remember that we are biased. We only treat crystalline structures. We ignore glass, which is sad, no? Glass is a beautiful material. Have you guys ever seen glass being blown, glass blowing? You have? Online, I was going to say, my usual question is, have you seen glass being blown? And then my slightly more, how shall I put this, my more champagne question is, have you seen glass being blown in Murano near Venice, which is an island near Venice? Who's been to Italy here? Have you been to Venice? No! You've not been to La Serenissima. You've not, well, actually, I should. I've been to Italy like maybe 10 times, and I've never been to Rome. So, so the joke's, I guess, on me. But Venice is just, okay. Let me put in a plug for travel. I never traveled till I left India for a postdoc. But I have to say, science has given me the opportunity to travel. So I've even done things like been to conferences in Venice, which allows, a lot of people just visit Venice for the day. But if you're at a conference in Venice, you're staying in the evening. But Venice is just astonishing, right? It's this, no other word. You take the train there, or even if you land in the airport. You land in the airport, you come out of the airport, what do you see? Water. You get into a boat. The train station too. The train pulls in, and if you're looking out of the window, you're like, yeah, it's going through, there is some water here. But the train pulls in, and you come out of the train station, and you're on the Grand Canal. It's like nothing else, no other place on earth, right? Anyway, near Venice is the island of Murano, which is very famous for glass blowing. So we don't discuss the structure of glass, maybe briefly, but mostly we discuss the structure of crystalline matter. And I'm going to do it from first principles, right? In a very simple way. So if all this is familiar to you, forgive me. So what we need to consider is that all crystalline materials have something called a unit cell. So for example, if I drew out the structure of perovskite would have these large cations, say, in the corner. There are other ways of drawing this, but one way of drawing the perovskite structure is that there are large cations in the corner. There's a small cation in the center of the unit cell, and that small cation is 6-coordinate with anions. So these are the anions. The anions sit on the face of the cube, and the cations sit in the center and the corners, and these anions the anions form an octahedron around the central atom. So this is the perovskite crystal structure. I'm sure many of you have seen this before. So one way we think about the structure is it's a cubic box, at least if it's the cubic perovskite. We think of it as a cubic box. The cubic box has atoms in the corners of the cell, and these atoms are shared with the next cell. So the next cell is going to look like the next cell is going to look like that, right? So every corner atom is shared with other cells. The central atom is not shared. Every face atom is shared at least between two cells. I hope you see this. So if you count up the corner atoms, there are 8 of them, And each one of them is shared between how many cells? How many do you count the corner atoms are shared with? 8. Do you count 8? Does everyone count 8? 1, 2, 3, 4 in the plane. Here, 1, 2, 3, 4 in the plane below. Right? Do you count the center? So 8 times 8 corner atoms is only 1 atom. So there's one blue atom. Let me call this the A atom. Let me call this the B atom. And let me call this the O atom. Or the X atom. Oh, actually, let me call this, let me be a little more disciplined. Let me call this AMX. Okay, so we've counted one A atom and one M atom. How many X atoms are there? How many X atoms do you count? The reds? Three. How do you explain the 3, please? Because I see 6 of them, but explain the 3.
The red atoms, they're on the face of the cube, so they get cut in half.
Cut in half, exactly. Each red atom is shared with, so it's AMX3, right? Right? And this is the perovskite. This is the cubic perovskite. They don't have to be cubic. They usually are not. But we call this a cubic perovskite, the perovskite. And by the way, perovskite, that's the name of the mineral. We'll come back and talk about this mineral. It's a very important mineral. Particularly, it's a very important mineral for understanding the structure and properties of materials. So this is the structure of perovskite, and this is one unit cell of the perovskite structure. So let me now ask you this question. If I had to depict the structure, how many parameters do you think I would need? How many descriptive parameters do you think I would need? For example, I would need the identity of the atoms. I'd need to know what the A atom is and what the M atom is. Yes? Example of a cubic perovskite is barium. Example is barium zirconium oxide. So the A atom is barium, the B atom is zirconium, and the X is oxygen. So how many parameters do you think I would need to describe the structure? Let's start counting. Do you agree that I would want to know what the length of the unit cell is? Yes? That's one parameter. Because it's a cube, I only need one parameter. I know all the angles are 90 degrees. To define a cube, I just need the length of one side. Yes? What about the positions of atoms? Would I need to know the position of the barium? Where is the barium? At the corner, 0, 0, 0. Yes? Would I need to say that the barium is also in all these other positions? No, because I can recreate them just by repeating the unit cell. Correct? Would I need to know that the M atom is in the center of the cell, 0, 0, 0? Sorry, half, half, half. And that's all I would need for the M atom. What about the X atom? How many X atoms would I have to specify, in your opinion? Okay, so you have taken crystallography classes before. So some of you should be able to answer this question. How many? But if you can't answer this question, that justifies my teaching. How many X atoms do you think we have to specify? 3? Who said 3? 3 is a good guess. What if I told you you only have to specify 1? What are those transformations called? What are those relationships called? What kind of relationships are they between the different X atoms? So this is the idea of symmetry, right? So this is where we bring in the ideas of point group, space group. But let me tell you one very simple thing. It's a cube. When I say it's a cube, I don't just mean that all the angles are 90 and that all the edges are the same length. I also mean that all the faces have to be congruent. The faces have to be identical. So it cannot be a cube with just one red atom in one face. So if I put one red atom in one face, it automatically has to go to all the other faces. Otherwise, it's not a cube. So in fact, to specify the structure of AMX3, cubic AMX3, I just have to say A is at 0, 0, 0, M is at 1 half, 1 half, 1 half, and X, for example, I'd have to say it's at half, half, 0. And X at half, half, 0 automatically becomes half, 0, half, and 0, half, half. So I get 3 of them, but they're symmetry related. Okay, and the way I get all of this, and then of course I would need to know the cell parameter. Cell is equal to A angstroms. Typically in an oxide perovskite, it will be somewhere between 3.9 and 4.2 angstroms. And I would need one more piece of information. I would need to know what the space group is. So I would say this is PM3 bar M, and this is space group number 221. Okay? Am I right about 221? I hope I'm right. I might have to verify the number. I should know this, but I might have to verify this. Okay, and I'll tell you what we're not going to do. By the fact that that's space group number 221, you may guess that there are a lot of space groups. There are, in fact, 230, right? So obviously, we're not going to learn how 230 space groups work. We're going to learn how a few work. But if we start in one dimension instead of 3, life becomes easy. Because in one dimension, there are only 7 line groups. There are 7 line groups in one dimension, 17 plane groups in 2 dimensions, and 230 space groups in 3 dimensions. What about 4 and 5 dimensions? 4, 5, and 6 dimensions. Do you think anyone cares? Do you think anyone cares about, say, 6 dimensions? You can imagine, you may be able to guess, that there are enormous number of 6-dimensional groups, right? Is it relevant for us? Actually, it is. Believe it or not, there are people who will tell you that it's easier to do work in 6 dimensions and project into 3 dimensions from 6 dimensions. Do a mathematical projection, right? It's easier to do that than to describe some things in 3 dimensions. Well, we'll discuss that at some later stage when I tell you about quasi-crystals. But a lot of quasi-crystals have crystallography that makes sense in 6 dimensions. It doesn't make sense in 3 dimensions. Have you heard of quasi-crystals? We'll maybe talk a little bit about them during the course of the class. So what I'm going to show you today is I'm going to build up this edifice of crystallography starting with the symmetry operations that relate things to each other. And you will see that the symmetry operations operate inside of the unit cell, but once you have the unit cell, you just tile the unit cell along x plus x minus x, plus y minus y, plus c minus c to get the structure. Okay? So let's start by learning the plane groups. So I'm going to erase this. And I'm going to start by talking about the plane groups, the line groups, the 7 line groups. And already in 1D, we're going to learn a few crystallographic operations. So 7 line groups in 1D. So the first line group is what we call, so first of all, I'm going to define a motif. This motif, you can think of it like an atom or a set of atoms or a molecule in the unit cell. And this is my motif, right? And the first line group that I'm going to call P1 does nothing. There is no symmetry operating on the motif. So all you can do with the motif is repeat it. So you'd get the whole crystal by repeating this motif again and again. And then you see that the unit cell is somewhere like this, right? You can also change the origin, but that's the unit cell. Unit cell. Unit cell or you could call it a unit length. Okay? So you get the crystal by just tiling, repeating it in the plus x and minus x directions. Okay, and in fact, a one-dimensional crystal, the greatest example of a one-dimensional crystal is the number line. You're used to number lines in mathematics. You know that anything between 0 and 1 is exactly repeated between, say, 965,487 and 965,488, right? And that's crystallography. Think of the unit length in a number line like the unit cell in a one-dimensional crystal. So do you see that there is no symmetry operation here? Maybe you don't see it. You'll see it when I show you a symmetry operation. Okay? So let's consider the line group PG. And by the way, the order in which I'm presenting these may not be the correct order, may not be the formal order. What PG does is this G stands for something called a glide. And in one dimension, a glide is a translation and a mirror, or a translation and a flip. Okay? This is called a glide in one dimension. There are also glides in 2 and 3 dimensions, but in one dimension, what the glide does is it takes this object and then translates it and makes it this object. Whoop. Translate, and then this is now the unit cell. So in the next unit cell, we will have something that looks like that, and something that looks like that, etc. Okay, so this to this is the G glide. This is now the unit cell. Okay, so in the P1 structure, there's only one motif per unit cell. In the PG structure, there are now 2 motifs per unit cell. Right? But what is important to note is that the symmetry operation here, which is the glide, operates within the unit cell. You can say, wait a minute, it also operates outside of the unit cell, because this whole thing, you could think of going like this. So you can treat everything as being related by symmetry. But the important thing is inside the unit cell, it's related by symmetry. Okay? Everything else is done by translation. In 1D, it's done by translation. In 2D, it's done by tiling in 2D. And in 3D, it's also done by tiling. So that's PG. Okay? It's a G glide. There's also a P2. And a P2, you know what 1, 2, 3, etc. mean in crystallography? Rotations. So a P2 is a rotation. So if I have an object like this, I can create the rotation here, and the rotation is usually shown, at least in 3-dimensional crystallography, the rotation is shown by an object that's shaped like this. Like a little bit like a football, right? And you know, the technical term for such a shape is a lozenge. A lozenge. So I put the lozenge here, that's the symmetry operation. So what it does is it does a 2-fold rotation of the object. So this object is rotated by a 2-fold rotation. What is an n-fold rotation? N-fold. N-fold rotation is a rotation by 360 by n. 360 degrees by n. So 2-fold rotation is a rotation by 180 degrees. Okay, so if I have an object like this, the 2-fold rotation makes it like this. Right? So P2, so this is within one unit cell. In the next unit cell, you'll see. Okay? So we've learned already there's a symmetry operation called a glide, which is a translation plus a rotation, a translation plus a flip, like translation plus a mirror. I'll show you what a mirror is. We also have an operation called a rotation, which is a rotation around a certain axis. And in this particular example, the axis of rotation is perpendicular to the propagation axis. Okay, the axis of rotation will become important. In this case, the axis of rotation is perpendicular to the propagation axis. Okay, so we have 3 of our 7 line groups. The fourth one is going to be a mirror. This is called PM. So if this is my object, the mirror is going to take this object and make it look like that. Okay? And this mirror lies in the propagation axis, right? The mirror is basically here. So this thing is flipped around like this, so the mirror lies like this. So this is like a parallel mirror, but you can also have a perpendicular mirror, and unfortunately it is also called PM. So what the perpendicular mirror does is it takes an object like this and then reflects it like this. Takes an object like this and reflects it like this. So when you have mirrors and rotations, you should ask, where does the mirror lie, or what is the axis around which I'm rotating? Okay, so how many line groups do we have? We have 1, 2, 3, 4, 5. Yes? So now, what is left? What is left, interestingly, are combinations. Okay? And what are the combinations? The first combination is P2MM, or just PMM. And you'll see that you will see something funny about this line group. If this is my object, there's a twofold axis here. Okay? The twofold axis is going to get the object like that. But now there is also the mirror. So the mirror is going to do this. Do you realize that there is some redundancy in the space group? I could call it PMM because they are both mirrors operating, or I could call it P2M, and it all amounts to the same thing. And this is often the case in a space group, that if you have a specification, you may not need every item of the specification. I could get this by saying it's PMM, I could get this by saying it's P2M. Any combination of 2 and M give you the other mirror automatically. Okay, or the two mirrors give you the rotation automatically. Okay, note redundant. I'm going to say note redundancy, meaning it's over specified. So the last space group I have is it's P2MG, and P2MG looks like this. Here's this object. Here's a mirror. Here's a mirror on this object. If I glide it, I take it here and flip it around, I get this object. And you see that it automatically gives me a twofold rotation. So here's the mirror. Let me draw the mirror like this. Here's the twofold axis, and here's the glide. Again, you see there is some redundancy. I could just say P2G and the M comes in, or I could say PMG and the 2 comes in. Okay, so guys, I hope you feel a sense of satisfaction, because without looking at my notes, I could actually reproduce these 7 line groups, which means you can as well. And it's a complete description of symmetry in 1D. So if you ever have a one-dimensional pattern, And where do you find one-dimensional patterns? Can you give me examples of where you find one-dimensional patterns? In clothes, in architecture? Can you think of something? Yes?
Would be just a single line of charge in the lattice?
It would, yes. But I'm not thinking about in a crystal. In real life. Like, let's look at a building. Let's look at the top of a building. Do we sometimes see an architectural pattern, right? Like carvings if you took like an older fashioned building, or sometimes, I think even PSPN or the physics building, there are tiles that they put on, and they put a pattern on the tiles, and those repeat in one dimension. Okay, those are sometimes called, the term in architecture is called a frieze, right? So, have you guys been exposed to the word lozenge before? You knew the word lozenge?
Well, for the cough drop.
Yes, cough drops. Good. Have you heard the word frieze before? Who says this? We can't learn English in addition to crystals. So, P2MG, P2MM, PM. Now, one of the things I'd like you to note is in these descriptions, these are considered higher and higher symmetries. This has the most symmetry, this has the least symmetry. And characteristic of going higher in symmetry, you get more and more replicas of the object in the unit cell. Okay? So please count. I'm going to call this Z, which means this is the crystallographer's notation for the number of objects in the unit cell. So Z is equal to 1, Z is equal to 2, 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 Z is equal to 4, Z. Do you agree? Yes? So, glides, mirrors, rotations. Are we ready for 2D? Are we ready for 2D? Remember what I told you about 2D? 17 plane groups. Right? 17 plane groups. We will not go through 17 plane groups. But we will recognize all of the symmetry operations that exist in 2D, what the new symmetries are. There is only one new symmetry concept in 2D which you don't have in 1D. I'll introduce that. Okay. And by the way, I will post notes that describe all of this in some detail. And if you're interested in this whole science, the book that I like a lot is a relatively inexpensive paperback, and you can find older editions of it. It's by a person called Hammond, and the book is called Intro to Crystallography and Diffraction. Needless to say, I don't prescribe this book, and I also don't believe in telling you that if you look at the right website, you can find a whole PDF copy of this book. That'd be wrong. So I won't tell you that, okay? So this is a nice book. And in this book, you will discover what happens in 2D. 2D, first there are 5 different kinds of unit cells. There are 5 different kinds of unit cells. What's the simplest unit cell in 2D? Oh, by the way, 2D, 5 different unit cells, 17 plane groups, 17 two-dimensional groups. Do you know what else these groups are called? You may be appreciative of this name. They're called wallpaper groups. Now, we don't use wallpaper very much, but you know what wallpaper is, right? Wallpaper is, if you look at old buildings, go to an old palace, for example, the walls will not be painted. They'll actually be covered with paper that has patterns on it. So wallpaper groups are patterned groups, okay? And if you want to like look at a very nice depiction of wallpaper groups with their crystallographic depictions, the Wikipedia page on wallpaper groups is beautiful. Okay, so 5 different unit cells. Come on, clue me in. Is this a good unit cell? What would this be called? What's that object called? If it's drawn properly. What's it called? It's not a trick question. It's a square. So this is A, and all angles are 90 degrees, right? What is this object called? So square. This is a rectangle. A, B, 90 degrees. And A not equal to B. Right? What is this object called? And this is a special object. A, 120 degrees. What is this called? Do you know what kind of a cell this is? It's hexagonal. Why do we call this a hexagonal cell? And the question is, why don't we use a hexagon? Is this an acceptable tile for two? Can you tile two-dimensional space with a hexagon? What's your answer? Tell us why you can't. Your answer is correct. You cannot tile. You cannot use the rules of crystallography and a hexagon. Why is that? Why is a hexagon not allowed? Let's try and tile with it, okay? We tile by going along x. We can do that. Going along minus x. What happens if we go along plus y and minus y? Does it tile? It doesn't tile. Because we are not allowed to move it sideways. We can only go plus x, plus y, minus y. Similarly, a triangle is not allowed. Hexagons and triangles are not considered crystallographic tiles. But this hexagonal tile, which is two equilateral triangles back to back, two equilateral triangles back to back. This is allowed. And this can actually take care of these situations. If you have objects that look like this or look like this, it can be taken care of with our hexagonal tile. So that's 3 different tiles. The 4th tile you may not consider. You may be a little surprised, but the 4th tile is called a centered tile, centered rectangular. Centered rectangular. So this is the new operation that you see. This is 90 degrees. A not equal to B. This is the new operation you see in 2D, which is called centering. The object that's at the corner automatically comes to the middle. Or in other words, any two-dimensional coordinate, and I don't have to remind you that our coordinate systems are always between 0 and 1. So typical coordinate in a unit cell is 0, 0, 0, 1, 1, 0, half, half, 1/3, 1/3. So it's always between 0 and 1. So what we do in the centering operation is to any coordinate within the unit cell, we add 1/2, 1/2. So to 0, 0, we'd add 1/2, 1/2. This would be 1, 0, we'd add 1/2, 1/2, so it'd take us in the next unit cell, etc. Okay? So it's called centering, and in 3 dimensions, centering becomes very important. There we have face centering, body centering, etc. We'll see that in a minute. Or maybe not in a minute, but we will see that presently. So there is only one other kind of cell that I've left out, and that one cell actually takes care of all of these cells. That cell is called an oblique cell. That cell is called an oblique cell, where you have an A, you have a B, A not equal to B, and you have a gamma. Gamma not equal to 60, not equal to 90 or 120. Okay? Gamma is any angle. And this is called an oblique cell. Do you agree that the oblique cell basically covers all the other kinds of cells, right? The oblique cell basically is the Ur cell. It's basically any two-dimensional system can be expressed in the oblique cell. Oblique. So, do you know what the shape is called? What is the shape of the oblique cell? What kind of a geometric shape is it? Say it. Poly? But polygon is any object with any closed object. I thought you were going to say another P word. What kind of a shape is it? Let me draw it carefully. I think I've drawn it carefully enough. What do you see about the opposite sides? Are they equal? Are they parallel? What's an object called if its opposite sides are equal and parallel? It's a parallelogram, right? So when you started saying I thought you were going to say parallelogram. So all these unit cells, all are parallel, is that double L? Parallelograms. All are parallelograms. Why do they all have to be parallelograms? Because when you're tiling, when you take this tile and you move it, this edge here has to sit exactly on top of this edge here, right? The opposite edges have to be congruent. They have to sit one on top of the other, otherwise you will not be able to accomplish the tiling. So these are the 5 different plane unit cells. These are the 5 different kinds of unit cells in 2D. And these 5 different unit cells are associated with the plane groups. And I want to actually make this important point of we should not judge whether the unit cell is, say, square or rectangular simply on the basis, or hexagonal, simply on the basis of the metric. If A is equal to B, if both edges are the same and the angles are 90, it still doesn't make a square. To be a square, it must also have a 4-fold rotation axis. 4-fold axis. In a rectangle, it's a 2-fold axis. In the hexagonal cell, it's either a 3-fold or a 6-fold. Okay? So the symmetry actually is important in addition to the shape. So don't just look at the shape and say it's a square or a rectangle. Similarly, when I spoke about this with the cube, when we looked at the perovskite structure, we said if there's oxygen on one face, it has to be on all faces. Otherwise, we don't call it a cube. Okay? All the faces have to be congruent. So, with this description of the 5 shapes of unit cells, how do we get the 17 plane groups? Well, I'm not going to go in detail through the 17 plane groups, but I want to say that we have the 17 plane groups. Have rotations, glides, and mirrors. Okay? In one dimension, how many different kinds of rotations did we see? We only saw a 2-fold rotation. In 2 dimensions, you already have some idea that we can have more than a 2-fold rotation. What's the axis of rotation here? I just told you, it's 4-fold. The axis of rotation here can be 3 or 6, depending. The axis of rotation here is usually 2. So, rotation axes, you're allowed 1, 2, 3. 1 means there's no rotation. 1 means it's a rotation of, okay? 1, 2, 3, 4, and 6. Are you allowed a 5-fold rotation ever? Have you ever seen a 5-fold pattern in a tile? You've not. You don't see 5-fold patterns in tiles? You don't see them in crystallographic tiles. But have you ever seen a 5-fold tile being used, say, in architecture? Interestingly, Islamic architecture has historically had examples of very interesting tilings. Those tilings have 5-fold axes. They don't fit into conventional crystallography. And that's actually the science of, it goes into the science of what are called quasi-crystals. So, in I think around 86 or 84 or 86, there was this paper that came out of a combination of authors from Israel and some authors from NIST in Maryland, Sheckman, Bleck, Gracias, and Kahn, and they reported that they had seen in an electron microscope 5-fold diffraction patterns. Eventually, this actually led to a Nobel Prize for Dan Sheckman from the Technion, which is in Israel, because he was the first person to sort of observe and describe this 5-fold symmetry. Those are materials that we today call quasi-crystals, and they don't follow the rules of normal crystallography. But normal crystallography, you must have only these rotation axes. You can't have other rotation axes. Okay? You can have lots of mirrors, you can have glides, but you can't have more other rotation axes than 1, 2, 3, 4, and 6. So, when you want to consider, and the notes that I will post and also stuff that you can look up, it'll give you examples of the 17 plane groups. This is if you look at the Wikipedia wallpaper page, it gives you examples that look like this, right? And I will not, well, maybe I'll give this as a homework exercise, but you can try and figure out where the glides are and where the mirrors are and where the glides are. And I can tell you from past experience that if I give these kinds of examples in a midterm exam, it'll give you a headache. Okay, so I will not do that to you. I'll give you simpler examples than these, but you can actually tell symmetry from these. And what you have in 2D, what you have for 2D, and I may give you a homework that depends on this. So again, this is from the Wikipedia page on wallpaper groups. It's like a flow chart. How to actually determine the plane group symmetry. You count the number of rotations, you see whether it's 1, 2, 3, 4, or 6, and then you count the number of mirrors, and you go down a flow chart. So if I give you a pattern and a flow chart, in principle, you should be able to tell me the plane group of the 17 plane groups, which plane group it is, right? For example, you may just see a 4-fold rotation and no mirrors, it's P4. You may see a 4-fold rotation and 2 mirrors, it's P4MM. Okay, those are examples. So we will probably try and deal with this just using, just through homework problems, but I won't spend time discussing 2-dimensional crystallography anymore, because I want to move to 3D. Okay, are we ready? Any questions so far? Please ask all your questions, because sort of good to sort of get this understanding before we go to 3D, because depictions are always better in 1 and 2. Yes?
So the shaded square on the corner, that is a 4-fold axis?
I was just indicating a 4-fold axis. Needless to say, if it's on that corner, it should be on all corners, right?
Okay, and then is the one in the middle also indicating a 4-fold axis? Or is that
Here?
Yeah.
No, this is a rectangle doesn't have a 4-fold axis. A 4-fold axis can only exist when you go by 90 degrees and you get the same structure, because 4-fold means 360 by 4, 90 degrees. But if you have one long axis and a short axis, it can't have a four-fold axis. So rectangles only have a two-fold axis.
Oh, okay. That's why it's a rectangle?
Yeah.
Okay, thanks.
Yeah. Okay, and if I have a hexagonal cell, let me actually depict something that's hexagonal. Let me erase this and depict several hexagonal cells. So there's one, there's another, there's another, there's another, and if I do my trick of treating them like two equilateral triangles back to back, here, for example, I see a six-fold axis, right? So I see a little hexagon there. Do you see that? So that's why we call it hexagonal, because you can actually use that to draw hexagons. Okay, so I'm going to erase the board and start talking about 3D. The important questions are, what are the new symmetry operations other than rotations and mirrors? What are the new symmetry operations rotations, mirrors, and glides? Does something new happen when you go from 2 to 3D? And yes, new things happen. Okay, there are two new things that happen. Would any of you have a clue as to what this is? Screw, did you say screw? Yes, that's exactly correct. Screw axes only happen in 3 dimensions. And screw axes, as the name goes, is a symmetry operation that involves a translation and a rotation. Okay? Anything else in 3D that happens that you don't see in 1 and 2D? By the way, who are inversion, and is there a more general form of an inversion? It's called roto-inversion, rotations with inversions. By the way, who's a chemist here? You're a chemist? You're a chemist? Have you done symmetry, group theory in chemistry? Oh no, you've done it? You've not done it. You learn about what the symmetry of molecules are, like point group symmetry, right? Like water is C2V, benzene is D5D. What is benzene? Do you remember?
It should be 6.
D6, yeah, D6D or D6H? D6H? Okay. So by that notation, do any of you know that notation? That notation, if you're interested, so the notation that says C2V, S4, ODOH, D5 what? D6, D or H? Whatever, D6, let's say D6H. This is called Schoenflies. And we don't use this notation in crystallography, used for molecules. In crystallography, we use something called Hermann-Mauguin. I think it's written like that, and this will look like 1 bar, 2 bar, M, 2M, 3M, etc., etc. Right? So just be aware that if you've learned this, there is a parallel here. But in this world, you don't have some of the rules that you have in this world. For example, in this world, you have molecules like ferrocene. This is the molecule ferrocene, right? And ferrocene, there are two kinds of ferrocene, but ferrocene has a 5-fold axis, which you can't have in a crystal. You can't tile an object with 5-fold symmetry. So Hermann-Mauguin is what I'm teaching you. So let's start off with roto-inversion, which is something that you don't have in 1D and 2D. Roto-inversion is a rotation plus an inversion. Okay, rotation plus inversion. So the simplest rotation, so inversion means if you have a point plus x plus y plus c, you flip it around the origin and look at it as minus x minus y minus c. Right? So, as a simple example, if you have a cubic cell and you have an object, say, in the middle at half, 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 and then you flip it around, you flip the unit cell, you flip it to minus half, minus half, minus half, and if the object remains the same, if same, then we define the symmetry as 1 bar. Okay, it has inversion symmetry. So symmetry, we say the symmetry exists if it's not changed by that operation. In other words, we just flip the object around some origin. Okay, that's 1 bar. What's 1 in contrast? 1 is you take an object and you do nothing to it. That's 1. You take an object and you change plus x plus y plus c to minus x minus y minus c. That's 1 bar. And by the way, this object may not be described by a single set of xyz coordinates. It may be an actual three-dimensional object like a molecule, in which case you have to take every part of that object and flip it from plus x plus y plus c to minus x minus y minus c. Okay? So 1 bar is inversion. So what is 2 bar? What is 2 bar? 2 bar is twofold rotation plus inversion. Okay, so 2 bar you depict as, for example, if you had an object here, I don't want to get confused. If you had an object like this along this axis, you rotated it by if you rotate if you rotated it around the center there, 2 bars of mirror, 2 bars of mirror, so you rotate it around the center there. Yeah, so if you have, let's say you have an object like this, you rotate it by 180 degrees and you flip it, you get the object to come somewhere here because you've rotated it by 180 degrees but you flipped it through this inversion, so this point becomes this point and this point becomes this point. So in effect, 2 bar starts looking like you have a mirror running through like that. So 2 bar is just a mirror. 2 bar is a mirror. 3 bar, the way to think about 3 bar is a Star of David. 3 bar is an object that looks like this. Okay, we can draw it on an axis. If you have an object that looks like this, you translate every point in this object and you rotate it by a 3-fold rotation, which is a 120 degree rotation. So it basically looks like 2 triangles Okay, so a threefold rotation would be this object comes here, this whole thing just rotates by a threefold rotation on a triangle is not going to change the triangle. But a threefold rotation of this object plus an inversion takes this point to this point, this point to this point, this point to this point. So a Star of David is, if you if you made a Star of David with two equilateral triangles. But where do you find this symmetry? It's quite a common symmetry. Do you know where you find it? In an octahedron. Do you know how to draw an octahedron? You could draw an octahedron in two ways, right? This is 3 bar. So octahedron. You could draw an octahedron like this. Do you agree that that's an octahedron? But if you look down a triangular face, an octahedron looks like this. If you look, say, down this face through that face, the front face looks like that, the back face looks like that, and these are all connected. So this axis, if you're okay, threefold rotation plus mirror. Threefold rotation plus mirror. What does 4 bar? How is 4 bar familiar? 4 bar you see in methane. Do you see 4 bar in methane? 4 bar is a fourfold rotation plus an inversion. Fourfold rotation takes is a rotation by 90 degrees and an inversion. So this is my methane dance. Okay? Carbon, hydrogen, hydrogen, right? I do a fourfold rotation. Have I rotated by 90? Yes? I invert. Hydrogen, hydrogen. 2 hydrogens here, 2 hydrogens here. Is that a methane? Yes? So that's 4 bar. The Schoenflies for 4 bar is S4, right? A tetrahedron. Did I just describe a tetrahedron? The corners of a tetrahedron are S4, are 4 bar. 6 bar is actually not uncommon in hexagonal space groups. It's a 6-fold rotation and an inversion. So these are all roto-inversions. Rotation plus inversion. The name gives it away. And it's good to remember, in my opinion, it's good to remember 2 bar mirror, 3 bar Star of David, 4 bar methane. Okay, then you remember these things. So that is the first new kind of symmetry we encounter when we go to 3D. We didn't have this in 2D because you can't have inversion in 2D because, well, you could in principle, but it's taken care of with other things. Other symmetry operations take care of it. So the other thing which was recognized becomes important in 3D are screw axes. So screw axes are shown with subscripts. So typically, screw axes look like this. They look like 2, 1. We don't have a 2, 2. We do have a 2, 3. 3, 1. We don't have a 3, 2. We have a 3, 3. We have a 4, 1, 4, 2, 4, 3. And by the way, these are related. 2, 1 and 2, 3. Oh, sorry. We don't have 3, 1 and 3, 2. 3, 1 and 3, 2. These are related. Again, we don't have 5. We have 6, 1, 6, 2, 6, 3, 6, 4, 6, 5. This is related. This is related. Okay, so these are all the screw axes. Screw axes. Let's just consider them one at a time. For example, let's consider the 2-1 screw. We don't have that. We don't have 2-3. 2-1 screw, okay, is a two-fold axis, two-fold rotation, which is indicated by this sign, and translation by 1/2. So a 2-1 screw looks like this. Imagine that we are translating along the z-axis of the unit cell. This is z is equal to 0, and this is z is equal to 1, the top of the unit cell and the bottom of the unit cell. Okay, where z is, so I'm just assuming that z is the translation axis, and we're talking about x, y, z, right? And in crystallography, coordinates always just go from 0 to 1, 0 to 1, 0 to 1. Why? Because anything that's from 1 to 2 is just 0 to 1 in another unit cell. Or 2 to 3 is 0 to 1 in another unit cell. You understand that, right? It's like a number line. So if I have an object like this, I have to translate it halfway along the unit cell to this point. And what do I have to do? Rotate it by twofold, by 180. And again, the object always has to come back to the same when it's z is equal to 1. So z is equal to 1 is always the same as z is equal to 0. X equal to 1 is always the same as x is equal to 0. Y is equal to 1 is always the same as y is equal to 0. So 2-1 screw. What about a 3-1 screw? Explain now what a 3-1 screw is. It's a how many fold rotation? 3-fold, right? Translation by 1/3. So the 3-1 screw is going to look like this. You see what I'm doing? I'm giving myself 120-degree guidelines and all at z is equal to 0, z is equal to 1/3, z is equal to 2/3, z is equal to 1. And z is equal to 1 must be equal to 0. So imagine that I have an object here like this. I'm going to use the letter R, and I'm going to lay it down like that. Let me go clockwise. So this letter R comes here. Then here the letter R goes there. And then here it is back to here. I'm sorry, that's really not a very pretty diagram. So let's draw it in another way. Let's be super clever about this, and let's draw it looking down Z. I'm just going to draw 3 objects like this. I'm going to say Z is equal to 0. The object looks like this. Z is equal to 1/3. The object looks like this. And Z is equal to 2/3. The object looks like that. So let me depict it with a 3-fold dance. My 3-fold dance, I start here. I go clockwise, so clockwise means going this way. I go clockwise by 120 degrees, and then I rise again by 120 degrees, and then I come back here. Yes? That's not a good dance. I preferred my methane dance. Yeah. So a 3-1 screw is a rotation, a 3-fold rotation, and a translation along the screw axis, along the z-axis usually, by 1/3. What's a 3-2 screw? It's a rotation by rotation, threefold rotation, and it's the translation by 2/3. It's a translation by 2/3. So listen carefully. If I go up 2/3 of the way in the unit cell, what is my next rotation going to take me to? What's 2/3 plus 2/3? Sorry? 4/3. Can you write 4/3 in another way? 1 and 1/3. What is 1 and 1/3 in crystallography? 1/3. 1 plus 1/3 is 1/3. Because crystallography is always modulo 1. Do you guys do any computer programming? You know, do you know what the function modulo does? If I say 3 modulo 2, what does it do? It gives you the remainder. What is 3 modulo 2? What's 3 modulo 2? Or is it 2 modulo 3? I don't know. If I divide 3 by 2, what's the remainder? If I divide anything by 1, what's the remainder? It's something between 0 and 1. Right? So crystallography is modulo 1. All crystallography is modulo 1. Now, what did I just tell you? Your first rotation, okay, I'm going to do my dance again because my dance is important. Okay, I'm going clockwise. This is clockwise, right? My first rotation in my 3-1 screw takes me here. My second rotation takes me here. I just told you that with my 3-2 screw, my first rotation takes me here, and my second rotation takes me here. If you look at it, you understand that 3-1 and 3-2 are
mirrors?
Sorry?
Mirrors?
These are not mirrors. Well, they're mirrors of a certain kind. It displays handedness. One is a right-handed screw and the other is a left-handed screw. Which one is which? It doesn't matter. Crystallography can't tell, actually. You have to do extremely sophisticated experiments to find out whether something's right-handed or left-handed. Let's continue this in the next class because this is a very, very important topic, right? This is the topic that tells us about things like the origin of life, etc. Yes? And we never miss a chance to talk about deeply philosophical topics.